All right, how's it going, everybody? We are here on January 29th. We are going to talk about section 1.7 today. We're going to look at bifurcations in the plane. Um, by the way, I think that just as far as our like scheduling goes here, I think that I've been saying this one slightly out of order. In my mind, section 1.7 was our linear differential equations and the integrating factor. That's actually our next section, 1.8. So we'll hit that guy next week right there. I think I just kind of like misspoke about that in maybe our last video out there. So today we're going to talk about bifurcations, when things change. Next week's topics, we'll get linear differential equations, another analytic solving technique in 1.8. That one's super, super cool. We're also going to see in section 1.9 some substitutions that we can make to simplify some of our differential equations. You should, in a sense, think of this as sort of like the differential equations version of U sub. How can we rewrite something that we can't handle and turn it into something that we can handle by just a little bit of a transformation of variable? That'll be our section 1.9 stuff. And so that means that next week we'll be done with chapter 1. We'll get into chapter 2, start talking about systems of differential equations the week after that. So that'll be good. So today, bifurcation. This is a super, super cool topic. And the other cool thing about today is that on the one hand, we're going to do a little bit more math than we've done in the last couple days. On the other hand, we're not going to really do any calculus at all today. We're going to see if you really, really, really remember college algebra and if you are very confident in your factoring and your quadratic formula is basically what a lot of today is going to boil down to. So what we're looking at today with bifurcations is asking, what role do parameters play in differential equations? We've already seen some parameters floating around in some of our differential equations, and we can go ahead and reference our most used differential equation so far this semester, our basic population model here, our unlimited growth population model, dp dt equals kp. Here, this is a one parameter family of differential equations because there are an infinite number of values that k could take on, all of which would represent a new differential equation, right? So what we want to do is consider the fact that this is in fact an infinite number of different differential equations, and the question we want to ask is there any time that we might change the value of k and then see wildly different behavior if the value of k is changed? That would be a bifurcation here that we're going to see. So what I think we should do is we should graph this function of p versus dp dt for several values of k, and we should identify and classify the equilibria that are associated with this. All right. So if I'm thinking graphically here, I want to graph p on my horizontal axis and dp dt on my vertical axis. And notice that this is really just the same thing. If I'm saying dp dt equals kp, if I'm thinking of p as my x value and dp dt as my y value, this is really like saying graph all of these graphs right there, y equals kx. Well, this is just always going to be a straight line going through the origin because we have a y-intercept of 0, but that k being an unknown slope means that it's possible for us to have any sorts of slopes that are out there. So here's a bunch of possibilities that we could have for a whole bunch of different values of k, right? This looks like k equals 1, this looks like k equals 5, this looks like k equals, -3/2 or something like that, whatever. We've got an infinite number of choices of k that we could possibly consider here. All right, what I would like to do is say, in general, regardless of what k you're using, I want to know where our equilibrium are and how you'd classify them. And that's sort of the special thing that we want to get here. So our equilibria occur when dp dt equals 0. We're going to set dp dt equal to 0 a whole bunch today, or dy dt equal to 0 a whole bunch today, which really just tells me that kp is going to be equal to 0, which tells me that p equals 0 is our only equilibria that we're going to arrive at for p. Right? And what I want to know is p equal to 0 a sink or source? Well, what we learned in the last video is that we can take the derivative of our differential equation expression, kp, with respect to p, and we can find if it's going to be positive or negative here, right? So if f of p equals kp, then f prime of p equals just k. And so we're going to see here that if k is greater than 0, this is going to be a source. And if k is less than 0, this is going to be a sink, right? So here's the big deal about this. This differential equation on the whole is not that complicated. However, you should recognize that it might be the case that if we pick a parameter for k, it could end up having a wildly different overall long-term result associated with our solutions than other values of k. If we start with a k of 2, then what we're going to see is unlimited population growth. If we start with a k of negative 2, we're going to see population decay down to 0. Those are literal opposite behaviors. In one, we tend to infinity in long-term time, and one, we tend to 0 as t goes to infinity right there. Those are wildly different from each other. And it seems like the transition occurs right at k equals 0. Because at k equals 0, that's where we transition from the growth model to the decay model right there. All right? So here, a very, very small change in k can lead to a very massive change in long-term behavior of the solutions associated with this differential equation right here. So notice in this case right here that we can say for all initial p's, the limit as t goes to infinity, or for all initial p's that are greater than 0, because we're talking about populations, if we take the limit as t goes to infinity of whatever our solution is here, we are going to tend to infinity. However, for all initial p's that are greater than 0, if k is negative 0.001, we're going to see that our limit as time goes to infinity of the overall size of that population is going to go to 0, right? So this is saying we're growing versus we're decaying. Those two values of k are crazy close to each other, right? But one will result in a complete opposite type of long-term behavior as the other. So we experienced a massive categorical change in behavior of every single possible solution associated with this differential equation by just potentially varying that parameter by maybe a very little amount, right? And all we had to do is cross over that k equals 0, and everything changed about the long-term behavior of our solutions right there. So we are going to then say that, thus we say, I'm going to say thus, we say k equals 0 is the bifurcation value associated with the PDT equals KP, right? Our bifurcation values are values of a parameter at which we experience a categorical change in the long-term behavior of the solutions associated with that one parameter family of differential equations. And I keep on referencing one parameter family of differential equations. Hopefully it's pretty easy for you to visualize that we might have more than one parameter in a differential equation. There could be bifurcations associated with both. However, I also hope it's pretty easy for you to visualize that these get a little bit more complicated to talk about when we have more than one parameter going on out there. And so we will restrict our attention today to just one parameter family of bifurcations, one parameter family of differential equations and their bifurcations. However, this concept certainly extends to multiple parameters out there. So let's make a quick statement about this. In general, we shouldn't always just be expecting that small changes in parameter values will categorically change the long-term behavior of solutions. However, many, many real-world modeling techniques, what will happen is scientists, physicists, virologists, whoever the scientist is that's performing any modeling to make any type of predictions, will often build models that have literally dozens of parameters in them, and we need to fill in the appropriate value of that parameter. If we're talking about coronavirus, we want to say, what is the rate of infection for unmasked people? What is the rate of infection for masked people? What is the risk of, the mortality rates for these things? All of these are parameters associated with a particular virus, and we need to know all of these details about a virus to be able to make modeling predictions for the future. Well, part of the whole issue with coronavirus is that this is new enough that we don't have a lot of research that informs us of what values these parameters take on. Just because we're observing this virus, we kind of need to see it over years and in lots of different scenarios. One of the things right now, like my wife is pregnant. Well, there's been a couple very, very small studies that have talked about differences in how coronavirus affects pregnant women versus non-pregnant women. And some of them have made some kind of crazy statements that say it's wildly different, but they have sample sizes of like 20 pregnant women. Because how many pregnant women are going to want to get coronavirus to be a subject for this test here? Like obviously not very many. So the point is, in a lot of cases in science, we can build a good general model that we know is generally descriptive of a general case. But then when we say, oh, we're not just talking about virus transmission, we're talking about this virus. Well, now you've got to pick parameter values for all those dozens of parameters that are involved in your model. And especially when we're in sort of more of like an emergency scenario, like a newly emerged virus right here, we don't just know these values. And we also know that as the virus mutates, we'll experience changes in transmission rates, stuff like that. That's a parameter right there, a transmission rate, right? So the bottom line is, even the most advanced models used by the highest level scientists on Earth are at the end of the day very often just using, I'm going to just put it in quotes here, fancy guesses for the values of the parameters in their model, right? They're often educated guesses. They're often informed by data, but it's informed by like as much data as you have. And again, with coronavirus, not only do we not have very much data, but also we're seeing, significant government suppression of data being collected because it looks bad. And unfortunately, I care more about science than looking good. Which means that we're all in a tough spot because of that. We could have handled this situation better if our government liked data, but it doesn't apparently. So the bottom line is, if we go guessing a parameter value and we say, hey, it seems like this virus has a transmission rate that's going to suggest that we should choose the value of 25 for this given parameter. Well, if that parameter actually experiences a bifurcation at 24.5 in our model, then that really, really, really matters to me that I know that, because that might suggest to me that my guess of 25 is going to provide us wildly different predictions than if I had guessed 24. And if I don't know that there's a bifurcation occurring at 24.5, it's not obvious to me that choosing 24 as my guess and 25 for my guess might lead me to wildly different conclusions about the long-term behavior. So kind of what we're saying here is, since it's often the case that high level modeling things that are going on with scientists involve guesses for parameter values, we have to know what the bifurcation values are that are associated with each of those parameters to make sure that we understand that our guesses might be near to those, and therefore that we might want to look more closely, right? Because again, if you're guessing 25, you're probably thinking it doesn't really matter that much if you guess 24 or 26. But if there was a bifurcation, a wild change in long-term behavior as we crossed over 24.5, you need to know that as a scientist to know that your model might be wildly wrong instead of just a little bit wrong at the rounding error in the long-term behavior, right? So identifying when these bifurcations occur is important for sort of understanding the goodness of the models that we're creating, the goodness of the guesses that we might be using for the parameters that we're plugging into these models here. So this is just like, why do we care about these right here? It's sort of our motivation. So let's go ahead and consider the one parameter family of differential equations, this guy right here. And what you can see is that we have a parameter of mu. So rather than just calling this general thing f of y, we're going to specify that this is a one parameter family dependent on mu by saying it's f sub u of y right here is the function that we're looking at. And what we're going to do to analyze what happens as mu changes here to visually see the bifurcation is we're going to draw a whole bunch of phase lines right now. All right. So last class what we did is we said, rather than drawing entire slope fields for autonomous differential equations, notice that there's no t in this thing, so it's autonomous. There's no reason for us to draw an entire slope field for an autonomous differential equation. Every column is going to look exactly the same as every other column. In each row, the slopes are all the same. So it doesn't matter to just keep on drawing the repetitive thing from left to right. So we just drew one vertical slope field line, which we called a phase line. What we're going to do now is we're going to allow mu, the parameter, to vary. We're going to use all these different values for mu, and we're going to draw the one phase line for each of the mu's, and we're going to stack them all up right next to each other, and we're going to see a nice sort of diagram emerge from this. So kind of realize our big picture thing that happened here. We're taking our t's and our y's to produce a two-dimensional slope field. We're recognizing that because there is no t in autonomous equations, there's no real reason for us to make a two-dimensional graph, so we collapsed it on down to a one-dimensional graph. Now we're seeing that if we introduce a parameter, now there actually is a reason to have two dimensions once again, because y's are going to change and mu is going to change. So now we're re-extending the one-dimensional graph that we collapsed down to in the last section into lots of those representing a two-dimensional, what we're going to call a bifurcation diagram, because it's going to help us see what values of the parameter cause the big change to happen at. So let's see like the little bit of algebra that we're going to do to make these guys happen. Um, so let's start at like the leftmost one, right? So if mu is equal to -3, then I'm going to be looking at y squared minus 2y minus 3 as my f of y right here. And I want to know where are their equilibrium. Equilibrium are going to occur when our differential equation is equal to 0. So that's at y squared minus 2y minus 3. I can factor this guy and see that this is going to be y minus 3, y plus 1. And that tells me that this guy should be experiencing equilibrium at 3 and at -1. So I think I can go ahead and draw my first phase line here. We should be at -1. And by the way, I'm going to draw a axis right here, a y-axis. We're at -1. Okay, here's what I'm really going to do. Let me do this. Here we're at -1, and here we'll be at 3 right there. And this is our y-axis right there. All right, so what I know is we've got equilibrium at 0 and at 3. I then think that we should have all increasing or all decreasing behavior on either side of these equilibria. So I can do things, for example, like plug in y equals 5, or maybe I should think about 5 right here. 25 minus 10 is 15, minus 3 is 12. So our dy dt is positive 12, so we're increasing when we're above this thing. Between -1 and -3, numbers like 0, if I plug 0 into this, we're getting -3 for dy dt. That says y is decreasing over time, so I'm going to get some downward arrows in here. And then if we plug in very negative things like -10, we can see that we're going to get things like -10 squared is 100. -10 here gives us another 20 for 120. And then -3, so 117. dy dt is definitely increasing. dy dt is positive 17, so we're going to get an increase down here for this guy, right? So it looks like I can go ahead and fill in this circle. I know that this is a sink. We've got everything pointing towards it. This is a source. Everything's moving away from it. So there's our first phase line that we're drawing, and I wanted to draw a whole mess of these phase lines here. I'm noticing that these numbers came out clean because this was factorable. I don't necessarily think that we're going to get nicely factorable things for all these guys here, but I do want to draw, maybe I want to build up my... And what I think we should do is let's pick out the easy ones where we get some clean numbers and see what that stuff looks like. So I'm just going to kind of build my setup now. We're going to draw a phase line for every one of these things. And what we're seeing here happening as we go from left to right is our mu value is changing, right? So we're really building like a mu y plane here, right? Where mu is the x-axis, it's changing from left to right. Y is the y-axis, it's changing from bottom to top right here. So I think another easy case for me to identify right here is when mu is equal to 0. So let me go do some more algebra over here. If mu is equal to 0, then we got y squared minus 2y, plus 0 is equal to 0 is our equilibrium locations. And that just tells me that y is y minus 2 is equal to 0. So we should be getting equilibria at 0 and at 2 here, all right? So over here, I'm going to add on maybe some more 0, 1, 2. So what I'm seeing here is it seems like at the mu equals 0 case, right, I jumped ahead right here. I easily found that 0 and 2 are 2 locations. And the thing that we're going to see is that this is essentially that same parabolic shape. We're going to get the same behavior right here. Again, I'm not going to sit here and do like a ton of arithmetic right here. If you plug in some values that are up here, we're still going to get positive values for dy dt. If you plug in some values in between these two, we're still going to get some negative values for dy dt. If you plug in some very negative values, we're still going to get positive things because squaring makes that positive and kind of overtakes the any constant that we might have. We're still going to get this guy right there to be a sink. And the thing that you should notice is as we've moved left to right, it seems like these two equilibrium are coming closer and closer together here. So what I'm going to do is I'm just going to do our kind of like soft version of this right here. What you should be picturing is that this is really just a parabola with a vertical shift term that's changing, right? So this is really just a parabola that's sliding up and down. I can see the two roots of my parabola right here, and what I know is that as this upward facing parabola moves upward, these two roots are going to sort of pinch closer and closer and closer together as it slides upwards, right? So what we're going to end up seeing here is we're going to end up seeing some, and this is going to be like some square root number right there that I don't quite know, right? But they're going to move a little bit closer together. They're going to move a little bit closer together. Right? Now I'm struggling to draw this like well based on my setup right here. And where's the next one that we actually know? I think the next one that we know is at mu equals 1. At mu equals 1, we're getting y squared minus 2y plus 1 equals 0 for our equilibria. And what do you know? This factors into y minus 1 times y minus 1. Well, notice what just happened here. We only have one equilibria now. Now that mu has gotten as large as positive 1, there is only one location where we actually experience no change, and that's when y is equal to 1. And so it seems like there should be that an equilibrium there, right? Now, by the way, gosh, these diagrams are so bad right here. I wish I had I don't know. These are tough to get drawn right here. We're going to see a nicer picture of this down below. I'm going to kind of condense this information. Now I ask myself, what happens if I plug in values above y equals 1 and below y equals 1? Well, I mean, this is just the same thing as y minus 1 squared. I don't care what you plug into this. We're going to square it. We're getting a positive number for every single output when mu is positive 1. So this is always going to be increasing. And notice that that kind of makes sense. It seems to me like what just happened right here is these two equilibria, they just came and they just pinched together and joined up as one. In fact, this is even a node right here, right? We've got things coming into it from one side, but we've got things leaving it on the other side. Those two equilibria literally just came and joined together as one right there. And you should notice that below the equilibria we were increasing, above the other we were increasing. Well, now that they've mashed together, we've just pinched out all of the decreasing area right there, right? Now what happens when mu equals 2, mu equals 3? Well, I'm not going to do the algebra here. I'm going to draw the graph. I know that when I look at this graph right here, we're going to see a parabola that's entirely above the x-axis. There is no way to get out a negative number from that equation right there. It's exclusively going to be positive. So what we're going to see now is there are no equilibria. We could go to the quadratic formula, find that there are no roots associated with that guy there. It's just going to be positive forever. Okay? So from this diagram, it looks to me like the bifurcation occurred at mu equals 1. Right? This is where we transition from having two equilibria for our differential equation to one equilibria to no equilibria. And it looks like that transition happened there at mu equals 1. That's exactly where we transition from 2 to 0. Right? Briefly, I think that we should go just watch this happen right here. Right? Let's see. Hey Freeman, both right here. This is for this is teaching a college differential equations class, but I'm certainly streaming this live for any of the people that are interested in kind of checking out some other things here. So if you're interested in watching some live lectures, I'm teaching trigonometry, calculus 2, and differential equations, and these will be live on Twitch and then recorded later for all of my students that don't watch live and watch this guy after the fact here. So join us. So I'm going to pop into Desmos here, and I'm going to graph basically exactly what we have, right? We had y squared minus 2y plus mu. I'm going to do x squared minus 2x plus, and I'll just call it a for Desmos right here. All right, exact same equation. Here's the, and in fact, here we go. Desmos always starts our slider at 1, and we can see this is our 1 root. If we have a values that are less than 1, we have 2 roots. A equals 1, we get 1 root, and for all values of a beyond, we get no roots. Those are literally exactly the equilibria that we're looking at. This is a bifurcation that we're experiencing right here. 2 roots, 1 root, no roots. That's a bifurcation occurring when the parameter takes on the value of a equals 1. We're just recognizing this as a descriptor of our long-term behavior of the solutions to our general differential equation, rather than as just an algebra topic and just the number of roots of a quadratic. And by the way, I'd like to say, teaching algebra for me is hard because every time I'm teaching things like counting the number of roots of a quadratic, it's like, who cares? And in algebra class, I have a hard time motivating why anybody would care. It's not until we actually go and take a calculus class that we can see, oh, this is describing to us, are there any stable solutions associated with this differential equation right there? What I want to do is I want to combine this into one single bifurcation diagram right here. And again, I know let me click back over. I know that my bifurcation diagram got a little sloppy right here, but what we can see is if we just try to draw this as one nice graph right here. I guess I want to go from -3 to +3 out there, is that we can see that we experience, sorry, 1 second, I want to see my, oh yeah, okay. So here's my other kind of important thing right here. Our bifurcation value, that's sort of our term for where the bifurcation occurred according to the parameter. Our bifurcation location, that also includes what was the value of that equilibrium at that point. And so this is where I'd say mu comma y is equal to one comma one. Freeman, I'm not recalling my definition of Lipschitz here. What's your question there on the Lipschitz here? If you could describe that a little bit more. So what I'm seeing here is that we've got a y-axis and we've got a mu-axis here. And it seems to me like, see on y and on mu right here, is that I can see this bifurcation is exactly right there at mu equals 1, y equals 1. And I can see our parabolic. So this graph is all of the possible equilibria that we're actually experiencing out there. Right? This is sort of a graph of equilibria on the dots right here. Differential continuity. If we're talking about differential continuity, this is derivative and its partial derivative with respect to y is also continuous. Okay, I don't want to draw that right there. The point is, for filling out the remainder of my diagram right here, that we see that all of our solutions are going to be increasing when mu is greater than 1. We're seeing that we're always going to have decreasing solutions when we are inside of this parabola here. And we're going to have increasing solutions outside of the parabola here. And increasing towards the parabola here as well. So it seems to me like what we're really seeing here is that this is really like a string of equilibria that are all sinks because we are converging towards them. And these are all sources out here. So these dots are not typically on these bifurcation diagrams right here. I think it's more typical to give like dashed lines and solid lines right here. But the point is we can sort of, in a sense, collectively take all of our one-dimensional phase lines right here and can combine them into one complete diagram for mu and for y to say things like, if our parameter increases beyond mu equals 1, there are no equilibrium. We can see that a stable equilibria does exist for all mu less than or equal to 1, or excuse me, less than 1. So we can kind of make some general observations here, right? Right, and at mu equal to 1, we had a node, right? So there wasn't the stable equilibria there. There wasn't a sink. There was a node right there. Yeah, Freeman. So you're talking about there being the potential to tend to infinity in finite time? Is that what you're talking about? Um, I'm trying to think about what our solutions will end up looking like for this guy right here. we're solving this guy, we're going to get things like our integrals of 1 over, like, like picturing our solutions here. So we're going to get some trig things on coming out from this guy right here. And so the general idea of it is certainly plausible. And in fact, we looked at some examples like that last video where we can't talk about long-term behavior as time goes to infinity because we've escaped off to finite or off to an infinite value of y in a finite amount of time. It's certainly the case that we want to identify when that can happen because that's typically not representative of real world scenarios where things like diverge to infinity in finite time right there. And so certainly a thing to have some awareness about when we're looking at our real world modeling here. It's often like our red flag, like if we do experience that type of behavior here, it's typically our indication that that might not be a good model for our real world equation right there. So in this case, I would say that this is, in a sense, a purely algebraic or theoretic example right here. We are going to look at some examples of some population models at the end, and that's kind of why I'm making the statement down here. We really care to know when do we have a stable equilibrium. If what we're trying to do is model populations, it matters that we know that there is a stable equilibrium that population could live at and that the current population might tend towards that. On the other hand, if there is no stable equilibrium, then that means that probably our population is in trouble, which is what we're going to see in kind of our final example of the day today. So what I want to kind of see here is that this was like a bunch of work, right? This required me to do algebra like 6 times right here, which I kind of like hand waved through, but certainly we could verify with some not very exciting algebra and arithmetic. The question is, could we have identified this information easier? I don't want to have to draw 9 phase lines and then jam them all together for me to identify a bifurcation value. What we're kind of recognizing here is that since this was a quadratic differential equation, and since you know how to determine how many roots a quadratic has, it seems to me like the answer should be yes. We can just go ahead and do some algebra here. So what I'm going to do is I'm going to hit up my dy dt equals y squared minus 2y plus, right, we're at plus mu, right? And I am going to take that to the quadratic formula, and we're going to determine that y should be, according to the quadratic formula, negative b plus or minus square root b squared minus 4ac all over 2a. Right, so we're going to get it looks like that 4 gets factored out as a 2, so I'm going to get 1 plus or minus 1 minus mu. And what we can see from this is that if mu is, let's see here, greater than 1, then we do not have any real solutions, right? If mu is larger than 1, then we're getting negatives underneath the square root, so there's no real roots. If mu is equal to 1, 1 real root. If mu is less than 1, we get 2 real roots. So it seems like in the case of a quadratic right here, because we have the quadratic formula, we can really just look at our discriminants, right? Our discriminant. For the bifurcation value. That was pretty easy right there, right? So that helps us find that mu equals 1 is where the change occurs, right? It's where the transition point is. And I say importantly, transition point. It's not like some slow, smooth thing right there. It's that one number. Getting over that number jumps us from 0 to 2 equilibrium. That's a categorical change in the results that we're seeing here. So the good thing about this now is that just by doing this little bit of algebra, what it allows us to do is it allows us to categorically classify all of the behavior of any of the solutions of any member of the entire family of differential equations just by having done a little bit of quadratic math right there. Oh, Freeman, yes, you're talking about the, okay, actually, Freeman, we did exactly that example last class, and exactly what you're saying, when we go to look at that in our ODE solvers, it gives us some wild graphs that have some problems, and so what you're talking about, I think the example that we did last class was looking at this guy right here, and the problem with this one is the dy dt gets infinitely large as y gets infinitely close to 1. And so our slopes get so big that every numerical solver is going to accidentally jump over y equals 1 which it really shouldn't, and it gives us lots of issues right there. So that was actually one of the ones that we just looked at right there. So exactly, the ODE solver issue is an issue right there, and we're going to attempt to fix that a little bit on our own. In a couple of weeks, we'll be writing our own like ODE solvers and doing a little Euler's method, doing a little Runge-Kutta-4 method to see if we can alter the parameters associated with those numerical solvers so that we don't get that accidental jumping over behavior, or at least identifying when it can occur, because as you're pointing out, we need to know when we should and shouldn't trust a random grapher that we found on the internet, because it will give us some solutions that are wrong because of that numerical jump over right there when it misses a point, because we need that continuity right there, like you're saying. So let's do a slightly more exciting example right here, and let's try and do less work, right? This was a whole mess of work right here. I'm trying to like do less work, but still get kind of the same results here. So let's see if we can draw a bifurcation diagram for dy dt equals y cubed minus alpha y. And as we kind of learned from the last one right here, and obviously I'm kind of setting some things up that are algebraically nice for a reason so that we can do some algebra to see what's going to happen right here. The very first thing I think to myself is, ooh, I can factor that. We're going to be doing it in Python, Freeman, if you are into that. Have you done any of that yourself? Or any programming in any language yourself? I'm going to do some sort of like introductory things with Python, and there's no anticipation of any prerequisite knowledge associated with that. So this will be sort of an introductory thing, but we'll build our own solution estimator and plot them and stuff like that. So I'm seeing here, this is really an alternate way for us to write our differential equation. And this is important to me. This says to me that there should be equilibria at y equals 0 and at y equals plus or minus square root of alpha. But there's some differences here. I'm again noticing a value underneath the equilibrium, or underneath the square root right here, says to me this isn't always going to be a thing that we can compute, right? If alpha is a negative, then we're not getting any real solutions. Right? So we can kind of make some statements here. So if alpha is less than 0, no other equilibria. If alpha equals 0, then we're getting no other equilibria. Because if alpha is equal to 0, then we're still just getting y equals 0 as our only other equilibria. But if alpha is greater than 0, we get 2 new equilibria. Julia, so I've been getting ready to poke my finger into Julia a little bit. I know that Julia is going to be right up my alley, because I know that Julia is syntactically structured a lot like Python, but built specifically to do some nicer math things. I've been debating doing that. I just think for introductory things, it'll be nice to do some Python stuff. But I do agree that Julia is a pretty good language to use for that type of stuff there. So here's what I am thinking to myself. I want to draw a bifurcation diagram. So I'm going to put my parameter on the x-axis and y on the vertical axis. Yeah, at that y equals 0, this is sort of like a double equilibrium at 0, exactly. So here's the kind of thing that I'm seeing. For all of our alpha values that are less than 0, the entire left-hand side of this diagram, there should only be one equilibrium, and it should be the one that is at y equals 0. That's right here, right? This y equals 0 is our only equilibria that we experience on the entire left-hand side of the graph. If alpha is negative, then we're getting things like a y squared plus some quantity, and that's not going to provide us any real roots. Let's decide what our arrows look like over here. I'm thinking that if alpha is negative, and notice, by the way, that I can just like pick a dot out there. Let's just like try and identify the behavior at that one dot. It should fully describe to us everything in this whole quadrant, because I'm only talking about negative alphas and positive y. And if I do this, then I should be seeing things like dy dt equals, and I don't know, pick y to be like 2, right? 2 cubed minus alpha is negative, so we're going to get like a negative 1 times that 2 right there. Well, that's going to give me 8 plus 2 is 10, and I don't care what the number is, I care that it's positive. So it seems to me like if from right here we're moving up, and if we have no equilibrium over which to cross to change our direction of behavior, I'm pretty convinced that everything in the second quadrant up here is going to have all solutions that are going to tend to positive infinity if our initial y value is positive and if alpha is negative. Conversely, we should see here that if we have a negative alpha and a negative y, right? This is my fourth quadrant. Let's say Q2. This is my Q3 consideration right here. And Q3 over here, well, again, I'm just going to like pick some arbitrary numbers right here. I see no other equilibria to cross over, so it doesn't really matter. I can pick -2 for y. Oh, wait a minute. Did I just do this wrong? Wait a minute. Am I being dumb over here? I just did that wrong, right? The y value. Oh no, y value was positive. Now my y value is going to be negative, so I'm going to pick a -2 cubed, minus my -1 times -2. Well, what's that? -8 minus 2 is -10, is less than 0. So we should be getting all solutions that are going to decay off to negative infinity if their initial value for y is negative and if a is also negative, right? We're making broad classifications about the long-term behavior of any initial condition associated with a broad set of parameters right here, which is big. So we've covered the whole left side. Now we want to talk about the right-hand side over here, right? I'm seeing that when alpha is equal to 0, we should still just have the one equilibria right there. But what we can see is that as soon as alpha becomes greater than 0, we're going to get two new equilibria. One at positive root alpha and one at negative root alpha. Notice, I'm literally going to graph this right here. I guess I wish I would have just done, I'm just going to do this. I'm just going to put this in a green box right here. This is literally the relationship between y and alpha as long as alpha is greater than 0. I'm just going to graph these two functions. There it is. There it is. It looks like for our bifurcation diagram right here, there are equilibria that are going to exist at y being the square root of alpha, the positive version, the top half, and at y equals the square root of alpha, the negative half down there as well. And don't forget, we still always, there's no value of alpha that makes our y equals 0, 1 go away right there. So we are retaining our equilibria that exists right here. And what's really important is that we stop and see exactly why we're getting these. We're going to go pop back over to Desmos in a second right here. But here's some other broad things that I want to say. This region over here all had increased to positive infinity as your long-term behavior if y had an initial value in this region here. What I'm noticing is that as we move from left to right, there is no equilibria that we're crossing that's suggesting that we're going to change our behavior above this curve right here. So I'm anticipating that our long-term behavior will remain the same. And similarly down here, there was no equilibria we crossed over to experience any change. So if we were going to change direction of behavior, there should have been an equilibria that we passed through that where that change occurred, and we didn't have that equilibria. So I'm expecting my long-term behaviors to remain the same right there. So it looks to me then like the only thing we have left to consider is, for example, what's happening at this point right here, right? And maybe I'll just draw this in let's just pick a new color here so that I can kind of stay vaguely organized right here. Let's mark this point in blue right there. And let's consider the point like a equals, let's pick a nice one for ourselves, 4. If I pick a equals 4, the green line is at a height of 2. So I just want to pick a y of 1. So alpha equals 4, y equals 1. I'm just picking one test point in a region to see what all of the behavior is like within that region right here. And if I do this, then I'm going to get dy dt equals, and I'm seeing here 1 cubed minus 4 times 1. 1 minus 4 is -3, which is less than 0. So that says to me, in everything in this region, we should be experiencing all of our solutions decaying down to 0. And similarly, and I'm not going to, again, there's just a mountain of arithmetic to do here today. If we would instead take a negative value of the same y, then you should see that we're going to get a -1 and a +4 right there for a +3. These are going to increase towards that equilibrium right there. So some very interesting things that I kind of want to like state about this thing before we go just kind of move along, right? We've done the math. Now we want to say, what did we learn from doing the math? And coming back to this diagram, this bifurcation diagram here, stationary points in higher dimensions. I can tell you that we're not going to consider higher dimensions, at least until next chapter. And when we do, we're going to look at 2-dimensional systems. We're going to ever so briefly look at 3-dimensional systems. As this is an introductory class, we're sort of getting our conceptual feet wet here, rather than building up into larger systems where the analysis gets a lot tougher out there. So some conclusions that I kind of want to make right here, or maybe I can even type this stuff out actually. Trifurcation, okay. Pardon read, I don't know if that was a joke or serious, but I will tell you that the name of this is called a pitchfork bifurcation. So yes, pitchfork bifurcations occur where we transition from 1 to 3 equilibria, and we retain the original one, but introduce 2 new symmetric ones. So we can see that y equals 0 is a source unstable equilibria for alpha being less than 0, but we can see that y equals 0 is a sink stable equilibria for alpha greater than 0. So I think one of the most important things to recognize here is that the classification of an equilibrium at y equals 0 changed depending on our parameter right there. It transitioned from being a source to a sink, stable to unstable, the y equals 0 equilibria. We were moving away from it on the left, we're moving towards it on the right. Right? The newly introduced equilibria seem to always be unstable. This is good. We can broadly classify the types of equilibria that we're seeing. So what I want to do now is I just want to pop over to Desmos and graph this thing just like we graphed the last one. And again, I want you to visually see that you already knew that this was going to happen because of what you knew about from algebra class right here, right? So popping over to the browser right here, we are looking at y cubed minus alpha y. So I'm going to get rid of that. We're going to do x cubed minus ax. I'm going to add a slider. Now, what you know, importantly, is that this cubic function here, right there, here's what I guess I really want to do. Just make that easy right there. What we know about the cubic function is that a equals 0, it has 0 slope. But notice, I think really important, that a equals 1, it has positive slope. So there's only one root, and what you know is it has positive slope through the origin, meaning that this should be representing a source because the derivative of our differential equation is positive at that point. So it should be a source. That's what we learned last section. And that's exactly what we saw. We saw that when our a values are negative, that equilibrium when y equals 0 is a source, right? It's sitting right there. Right? Now, when we come back over here, what we're seeing is that if we instead make our a values positive, what you know our other type of cubic looks like is, boom, where we introduce 2 new roots. These roots are always going to be symmetric with each other relative to this particular cubic right here because there's not a squared term that's also in it right there. And what you can see is that now, notice the really important thing here. Here, when we pass through the origin at y equals 0, we had positive slope, and therefore the equilibrium associated with y equals 0 is a source. But once we get our alpha value larger, now we pass through the origin with negative slope, and therefore it becomes a sink. Right? That's exactly what we saw last time. The derivative of our differential equation expression has positive or negative sign at the equilibria, determines if it's going to be a source or a sink right there. Further, we can see that we always have positive slope for the alternate ones over here, for the 2 symmetric ones. Therefore, they're always going to be sources right there. I do think maybe it's better to not have this guy right here to just see, like, we know what this smooth transition looks like, right? We go from just having 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. We notice that there's never a point in time where there's 2 equilibria. We immediately explode from just 1 equilibria, boom, 3 equilibria right away right there, right? And this is the transition that you know that cubics make. But now we're seeing this come up in a little bit more of an interesting sense here with the differential equations that we're looking at right here. All right, so, man, and I'm going to say this again, this is something I yelled at you guys about 2 weeks ago. Just stop and take a moment and imagine that you're taking this class in 1970. Way harder. Desmos makes it easy for us to visualize the occurrence of this bifurcation. Man, you get slider bars, and man, I talk about 1970. This didn't even exist when I was in undergrad, right? This is like really, really new. And you might say, oh, Desmos has been around for 5 years, maybe even 10 years, whatever. Calculus has been around for 400 years. For 99% of that time, people haven't had an easy way to visualize the things that are happening. So stop and take a moment and say, nice. Uh, we're the lucky ones. We get the easy visualizations for this stuff here. Nobody else in history has had what we've had to help ourselves picture this stuff here. Appreciate that. Okay, so we drew a nice bifurcation diagram. We can see that the bifurcation occurs at y equals 0. It's where we transition from 1 to 3, and we're able to classify what the sink or source status is of any of the equilibria for any value of alpha with just one diagram right there. Some really convenient stuff, right? It's a lot of information packed into that one graph that we've got right there. So now let's do the harder example here. This one's going to take us a hot minute. So we're going to do basically the same questions. Discuss the bifurcation status, draw the bifurcation diagram, blah, blah, blah. Let's analyze this differential equation with respect to its parameter mu right here. The really important thing that you should see is that this is, again, a cubic, but you should see that the role that mu is playing is wildly different. It is no longer a term that is describing sort of like the shift associated with one of our factors. It is the overall vertical shift component of the graph right there. Oh, hey, Freeman. I would be interested in checking that out. That is one of the biggest problems with ODE solvers, that they're very computationally intensive. And so finding out ways to not make them so, for my big complaint is I want Desmos for this class. And unfortunately, Desmos things don't work out great because it's way too much computational power to be thrown in browser for most of these ODE solvers to actually do a good job. So that is absolutely the direction that some of the more of the research things need to go in to make those solvers work out quite a bit better for us. So very cool. So what do we do here? How do we like generally analyze this? What I know is that I don't have a way to like just factor it and make some broad statements like we did above. But what I do know is that this should be okay. Sorry, I'm going to back off there slightly. What I'm going to say is let's think about the easiest case. And the easiest scenario associated with my parameter here is when mu equals 0. That's going to tell me that we're looking at dy dt equals just y times 1 minus y squared. I know what this looks like on my y dy dt graph. This is going to look like a root at 0 and a double root at 1, right? And I know that this is going to be a positive cubic because that's a negative getting squared to become positive times another positive. So I am thinking that this should be a cubic that is increasing until it passes through at 1, but then has passes through at 0, and then experiences a double root at 1 before it goes off in the positive direction again right there, right? This can help us understand what our phase line should look like associated with this guy right here. It seems like our dy dt is negative to the left of 0. It seems like it is positive between 0 and 1. And then it is positive again between 0 and 1 right there, right? I can see what my phase line looks like right there. I can see that we are going to have y equals 0 is a source. I can see our things moving away from the equilibrium at 0. And I can see that y equals 1 is a node, right? Things are moving into it from the left, but away from it on the right there. So real quick little bit of algebra right there. I've identified the equilibria associated with mu equals 0, and I've classified them, right? Now, how do I spell this? That's wrong. Perturb system. Right? So what I'm saying here is I want to come along and I want to bang on the desk now like we talked about last lecture. I know that I've got some equilibrium where they are, but I want to say what happens if we like wobble this system a little bit? If I just grab this thing and shake this thing a little bit, what's going to happen? Well, I want to vary this by a very small amount. I don't want to make some huge change right here, right? So if I'm going to say mu is a positive value for epsilon right here, then what I should be seeing is if I increase this thing by a little bit, then what I'm going to see is my solution here, or my dy dt graph right here is going to look like this, a y and a dy dt. And this looks to me like it has only one equilibria. It's occurring here at just a little bit to the left of 0, right? I can see that we have negative stuff and positive stuff here forever. And so we're going to get a source. Right? On the other hand, if my perturbation is a small negative amount, I only have to have a tiny bit of negative change right here to where our graph is instead going to do this, right? And importantly now, the one equilibria here has turned into two equilibria right here. My y dy dt, I can see the rate of change is negative to the left. It's positive here, it's negative here, and it's back to being positive here. So I'm going to get a source. I'm going to get a sink. And I'm going to get a source. Right? So it seems to me like mu equals 0 should be an equilibria, because if we vary ever so slightly above and below mu equals 0, we wildly change our scenario here. We go from 1 to 3 equilibria. I'm going to say seems like u equals 0, or sorry, I said it's an equilibrium. I meant to say it's a bifurcation, is a bifurcation value. It's where we transition from 1 to 2 to 3 equilibria. Right? And again, it looks like this equilibria has split in two. Right, to become the two equilibria that we're seeing crop up right there. It was one together, and they popped off separately into two different things right there. And if we go in the other direction, it doesn't even exist. Right? So it seems like we've identified a bifurcation value that's associated with this. Are there others? Now, what we just saw right here, and I know that we're just looking at my kind of crappy cubic drawings right here, but what we just saw was that because there was a local minimum right here, that we could either slide it up or slide it down to have that local minimum hit 0 times, right there, hit 1 time, or hit 2 times. Does it seem like that could occur somewhere else on this graph? Well, why not associated with the local maximum as well? Right? Right here, what I'm seeing is it seems to me like if we push this graph down enough, that rather than having our only equilibrium being on the left side of the wobble, that if we push this graph, if we shift it down enough, there should only be one equilibrium, but it should be on the right-hand side, because it should be that these two things are going to sort of poof away together, right? What I'm kind of visualizing here, and stick with try and do this in your head, because you should. Picture this graph right here and its relation to this one, right? We said that this one equilibrium right here sort of sprouted off into two. What I'm noticing is that of those two, this one on the left right here, if we keep on sliding this cubic downwards, this equilibria that's a sink and this equilibria that's a source, they're actually going to come together and then poof off into nothingness, and that this source should be the only thing that ends up surviving if our mu value is negative enough. Right? So it seems to me like there should be another one. Right? It's kind of what I'm seeing here is this. It should be the case that if we shift, let me see here. I'm kind of going to draw my. This is what I would draw if I didn't have my Desmos available to me. If mu is a large negative, then that means that according to our differential equation, we're shifting this whole graph down by a lot, right? So what I'm going to see is some graphs that look like this, one equilibria. Then as we continue to transition, this guy is going to get really, really, really close to being right here. And eventually, oh, excuse me, I guess I want to draw that one as being like the touching one right here. We should get to some bifurcation right there, right, where we went from 1 to 2. We know that at mu equals 0, we've shifted up enough that the bottom of this is touching the axis. And as we continue to shift up here, okay, this is a pretty bad series of drawings right here. But the point being that now we're getting to our scenario right here. So this is our bifurcation at mu equals 0. This is our, as we want to find this bifurcation. Nice, Freeman. That's pretty cool. I'm gonna click that open right here and take a look at that guy. Oh, you're doing it in Juliet. Good. This is gonna force me to actually look at some Juliet things instead right there. That's very cool, man. I will take a look at that after my videos here today. So kind of, again, what I'm seeing is I know that you guys can just picture this cubic, and as we slide this cubic up and down, you know that there's kind of two transitions. One where our relative minimum is at touching root, and one where our relative maximum is at touching root, and that there really should be some graphs. Okay, here's what I guess I want to do. Let me take this graph right here and just get rid of it. I want to take this graph right here and slide it over. And I guess that means I could, all right, I'm going to move some things around just so that my diagram looks a little bit less dumb right here. Let's show, oh, come on. I had a good plan right there, and then I just executed it poorly right here. My mu equals 0, and that there should be, let me get rid of this as well here. I wanted to draw one in between. In between, we have this scenario where we are actually doing our thing that a lot of cubics do, which is hit 3 times right there, right? So in between these two graphs, there should be some place where we have 3 equilibria. And then off to our 1 equilibria again out there once we've shifted it up enough. Right? This is our 2 equilibria and 2 equilibria. Right? So where we go from 1 to 2 to 3 to 2 to 1, the transition points are at 2. So those are where our bifurcations are happening. So what I'm saying to you is, I want to know where this guy is. We found just by sort of accident, by visual inspection, that mu equals 0 was going to be an easy one for us. Let's see if we can go ahead and do the algebra to determine where the other is going to be occurring here. And then we'll look at our population example as our final example there, right? right? It transitioned from no equilibria near y equals 1 to one of them, the node, to two of them once we'd shifted it down enough right there, right? We want to identify where's the other. It's at the relative max of f of y. Right? I know that if my f of y equation is my cubic, all I'm really trying to decide is where did that relative maximum occur. Unfortunately, all of you guys have taken Calc 1, so you know how to find relative maximum. Right? So what I want to do is take the derivative equals 0 and solve. So we've got our y times 1 minus y squared plus mu. I want to take the derivative with respect to y and set it equal to 0. This will help me locate where is that relative max. The mu part's going to go to 0. That's good. We're going to use the product rule for the other part here. I'm going to take the derivative of y and get 1 times 1 minus y squared plus y times the derivative of 1 minus y squared, 2 times 1 minus y, and apparently times negative 1 from the product rule right there. Set it equal to 0. A little bit of cleanup here. I'm going to factor out a 1 minus y. I'm left with a 1 minus y minus 2y. And that's going to give me 1 minus y times, let's see here, 1 minus y minus 2y is a 1 minus 3y equals 0. So that's going to tell me that y equals 1 is one place that we experience a relative max. I already knew that one. And y equals 1/3 seems to be the one that I did not know. What I want to know now is this is the y value of the bifurcation. We already found this one. Here we want the mu. That goes with this equilibrium. For the bifurcation. So what I'm going to do is I'm going to go ahead and set dy dt equal to 0 because I want to know where my number of equilibria change equals. And we're going to do our y times 1 minus y squared plus mu. And I'm going to go ahead and I'm going to plug in my 1/3 into this guy here. So I can find the associated value of mu that causes us to be at equilibrium. That's going to be 2/3 squared, which is going to be 4/9. That's 4/27. So it seems like if you choose the mu value of negative 4/27, then right at y equals 1/3 is where you'll have a node again. And if we wobble it a little bit, it'll either split into two if we go in one direction, or it will come together and poof into nothingness if we go in the other direction right there. So I think I now kind of know where all these are sitting for us to make a bifurcation diagram right here. And real quick, I want to kind of draw these again right here. When we're talking about our bifurcation at mu equals 0, that this was also associated with y equals 1. And what we were seeing right there was we were seeing solutions that did something like this. But there was some other ones that were doing things like this. There's 3 solutions. There's 1 solution, right? So there's 1 equilibria, 2 equilibria, 3 equilibria. And this point right here That's y equals 1. Right? Our bifurcation now at mu equals negative 4/27, that's associated with y equals 1/3. This is now where our graph is going to have the same type of action, but it's going to be with the other local max, right? This is where we're going to be seeing things like at y equals 1/3 right there, we're going to get our touching root. If we're a little bit above it, then we've now got 3 equilibria. If we're a little bit below it, then we've only got 1 equilibria, right? So there's 3 equilibria, 2 equilibria, and 1 equilibria for those 3 guys right there. And again, this location right here, that's our y equals 1/3. That's right when things are splitting, is when the equilibria location, or the equilibria itself is at 1/3. The value of mu equals negative 4/27 is the exact amount of vertical up and down shift to make it sit right there. If we shift it by more than negative 4/27, then it will shift up and we'll get 3 equilibria. If we shift it by less than negative 4/27, then it's going to be shifted down more and it's going to have only the 1 equilibria on the other. We have a bifurcation that bifurcates in both directions but is a double root. So are you saying like a double bifurcation? I mean, I could picture things like maybe like y minus 2 squared, y plus 2 squared. That should get a double bifurcation going on at mu equals 0 if we did a plus mu right there. And then we'd go from 0, jump immediately to 2, and then jump immediately from 2 to 4, and at no point would we have 1 or 3 equilibria in that case right there. So I think that the answer to your question is, I think the funny thing about the whole theme of today is like, well, it depends. How good at algebra are you? And that's kind of the answer to lots of these questions right here. I mean, we haven't done, well, okay, we finally did some calculus right here. It was just to find out where a relative maximum occurred. That wasn't even the thrilling part of the calculus that's right there. But these are kind of saying like, how super confident are you in all of our algebra things? And the other thing is that we're looking at tons of polynomial stuff right now, only because polynomials are our most algebraically manipulable things that we can like actually handle. Certainly it's the case that most interesting differential equations aren't built as polynomials. But again, conceptually, I think this is the easiest way to see these bifurcations is with these polynomials, which is why these are sort of our classic examples that are right here. So now what I want to do is I want to kind of like redraw our bifurcation diagram right here, but now I know where all the special stuff is happening. Right, so we know that these are where we've identified our bifurcations. Right. I know that if I shift this graph downward by more than 4/27, then we're only going to get 1 equilibria associated with that. I can't go drawing gigantic graphs for this guy. Hang on. Okay. And this is where we've shifted down a lot, and we're only getting the 1 equilibria right there. If we've shifted by exactly 4/27, then this is where our relative max has now come up and touched. We know that it's come up and it's touched right at y equals 1/3. And that we now have 2 equilibria. And it looks like, by the way, that should be decreasing, that should be increasing. So it looks like a node and a source. By the way, over here, these are all moving to the left, these are all moving to the right, so we get 1 source. In between these two is that nice little sweet spot where we're actually getting all 3 roots from our cubic. And it looks like here we're going to be getting, that's left arrows, that's right arrows, that's left arrows, that's right arrows right there. So it looks like we're going to get a source, then a sink, then a source. Say 1 source, 1 sink, one source. I know that's kind of a dumb way to write it, but it's kind of useful to know that they kind of go in that order right there. Now, if we keep on pushing our graph up even more, then we get to the point where we're getting this guy right here. We know that that's occurring at y equals 1 right there where the bifurcation occurs. That should be our increasing, or sorry, that should be our, oh yeah, increasing and increasing. But that's decreasing, so we're getting two equilibria where we're getting a one source and one node. And then finally, if we push this thing up far enough, then we're just getting graphs that look like this guy. In which case we're getting one equilibria, and that is one source. Right? So we can watch the bifurcation happen here graphically. This is, and I know that I should just go over to Desmos and do this, but like this is my by hand Desmosing right here, right? I'm sliding the slider bar for mu right here, and we're watching ourselves go from 1 to 2 to 3 to 2 to 1 roots of our algebra equation. But those are representative, those roots are representative of the equilibria associated with our differential equation here. The other thing that's really valuable to see here is that when we introduce this node generates one source and one sink. The sink is going to go join up with this source to become a new node over here, right? So the node creates two things. One of those things goes and partners up with something else to become a node that then itself later poofs off of existence later in those values of mu that we've experienced right now. So finally, let's go ahead and see if we can identify what our bifurcation diagram looks like. These can be kind of hard, except they end up being pretty reasonable if we see what our relationship's going to look like. Our curve is the equilibria. So what I'm going to do is to set dy dt equal to 0. That is our y times 1 minus y squared plus mu. Well, I'm just going to subtract off all this stuff. So this should be to me mu equals y times 1 minus y squared, or like a negative of that, right? I just want to graph this thing. That's literally all I want to do to graph my bifurcation diagram. But I'm noticing here that in our bifurcation diagram, we always draw our parameter as the horizontal and our dependent variable as the vertical. And I've got that switched right here. So this to me is like graphing x equals negative y times 1 minus y squared. So rather than having a cubic that has our traditional shape, we have switched our input and our output variables. So I expect this to be like a laying on its side cubic that we're visualizing here. I've identified the two important locations of my bifurcation, right? Those things are occurring at mu equals 0, y equals 1. That's a very special point. Mu equals 0, y equals 1. That guy's right there. I'm also going to be getting an important one here at mu equals negative 4/27, y equals 1/3. Mu equals negative 4/27, y equals 1/3. So there should be another special bifurcation location that occurs right there. And what we'll see is we're going to get exactly our cubic on its side, doing that for our bifurcation diagram here. And again, what we can go ahead and do is we can check out the fact that, for example, any value in the first quadrant, if you plug in a positive y and a positive mu, we're going to get positive times positive because it's squared plus positive. Well, all this stuff is all going up. Similarly, if we plug in a y that's down here, we're going to see that we're going to get some negative values for dy dt. And here's a thing that I know. I know that if mu is greater than 0, what's the one thing that's happening? If mu is greater than 0, then we have one equilibria that's a source. If mu is greater than 0, there's only one equilibria, it's right there, and it's a source. Stuff's moving away from it. I can just use this information to fill out my bifurcation diagram, right? Furthermore, if I go into the other side, if mu is less than negative 4/27, if it's more to the left than that point, then everything is also, then all those equilibria also sources. So I know I can draw all of these arrows sourcing away from this thing. Again, if I don't have an equilibria to cross over, they should never change. So it seems to me like these arrows should still be pointing down And these arrows should still be pointing up because they're part of the upward region here. They're part of the downward region here. So I am seeing, for example, that if we are between our two bifurcation locations right here, there should be 3 equilibria when mu is between this. That's our mu equals negative 4/27. This is our mu equals 0. If we're between the two, we do get 3 equilibria, and it does go source, sink, source. Source, sink, source. Right? We can see that chunk right there. Right? So I'm combining all of these ideas into one nice bifurcation diagram. So again, now you can tell me any parameter value that you think mu should take on, any initial condition for y, and I can describe for you the long-term behavior of any of the solutions associated with that differential equation without actually solving the differential equation. That's our value of our bifurcation diagrams right here. Yeah, so you're correct that we need the continuity of our differential equation right here to make sure that like nothing weird happens. We can only depend on that existence and uniqueness of solutions if we do have that our differential equation and its derivative are continuous. So I keep on making the statement that we can't experience any transition unless we have a root. And this is again just an algebra statement, right? This is like saying, well, the only way that we can change signs is if we pass through a root. Well, what we know is that that's not quite true. We can change signs by passing through a discontinuity as well, right? With rational functions right there. So the question in chat here is saying, is it not true that we only transition experience a change in direction of behavior over an equilibrium? And that's true. We could experience a change in direction over a discontinuity. But since we didn't have any discontinuities associated with this differential equation, we don't have any of that. But you're totally right. Just like we learned in algebra class, the only way that you change from positive to negative is either to go through 0 or to jump over 0. So we require either a discontinuity or a root, which in differential equations class is called a equilibria, to experience a change in direction. Otherwise, there's nothing that would cause that change, right? We've got to pass through 0 or jump over 0 to make that guy happen right there. Totally. So that one was a bear, but what that really took was a ton of algebra, and it took one little bit of calculus just to find a location on a graph. This was just me saying, find the location of the relative max of a cubic. So I took a derivative, set it equal to 0 to find one of the variables, plugged that variable back in to find the other value of the variable, found that the ordered pair, negative 4/27, 1/3, is exactly the negative 4/27, positive 1/3. And I think I'm just going to write a note about that as my kind of like concluding statement right here. Those are our two special locations where things changed out there. All right. So we haven't talked about any applications to this. We've just done a bunch of algebra today, basically. Let's do just a little bit more algebra, and let's talk about how this relates to like a real world population out here, right? So what we want to consider for this example is our limited growth population models. This isn't our unlimited exponential growth model. This is where we're saying there is a carrying capacity. There's a maximum size to this population, right? So that's our dp dt equals k p 1 minus p over n, right? That's the differential equation we've been using for that limited, or yeah, the limited growth model. As soon as our population size p gets larger than our carrying capacity n, then this factor turns negative, causing dp dt to become negative, right? But if it's lower than that, then we're growing. But we're going to add in a new modification to this now. We're going to say, let's change this up. This is relating how the population changes over time. So what I now want to suggest is we're harvesting things, right? This is like a fish population. This is like deer population. We're artificially, in a sense, extracting from the population rather than letting it do its natural stuff out there. So what we're going to do is we are going to be removing C members of the population every unit of time, which we're measuring in years. And I'm going to just say here, C is greater than or equal to 0. Technically, if you consider C to be negative, then it's like humans are adding artificially to the population. Awful difficult for us to do that in any meaningful sense. I mean, we do relocations and stuff, but that's not typically moving entire, schools of fish or things like that out there, right? So we're going to add on a harvesting term to this, a artificial removal from its environment, a minus a parameter C right here. Now, what should we expect to happen? Before we do any math here, let's first take a moment to consider what we should expect to see from the behavior of the solutions to this differential equation as C varies. If we have no harvesting, if C is equal to 0, then we expect our population will grow if it's small and decay if it's too big, if it's over its carrying capacity. However, we know that if we're harvesting a huge amount from this population, then it's never really going to have a way that it can grow, right? We're going to be crushing this population down to a small enough size that we're removing maybe more than it's growing by in a given year. Think about the fact that all C has to do is be larger than Kp times 1 minus P over N, and now our rate of change of our population size is negative, right? Right, so if C is too large, then dp dt is negative, and we should just experience a population decline to 0. This is not a math statement. This just says if we fish too much, there's no fish left, and if we don't fish a lot, there will still be fish. Pretty easy statement, right? This is fifth grade biology right here, right? Overfishing is bad. That's my one sentence description of what's going to happen right here, right, in non-math terms. So what we want to see is, does the math that we've been doing today agree with our intuition that overfishing is bad and underfishing is sort of okay? And then if we were really nice, we would figure out a way to not fish at all, because, man, there's not going to be anything left out there in the oceans pretty soon. So first, let's think about what this graph of this guy is going to look like right here. I know that this is just a quadratic. It's just an opening down quadratic, right? So Kp times 1 minus P over N is an opening down quadratic. And I know that C is a vertical shift term. Right? So I can basically draw the whole bifurcation here. I know what quadratics do. I'm good with quadratics, right? So if we think about what's going on when C is equal to 0, we should expect there to be a root at 0, a root at n, our carrying capacity. We expect to experience growth if we're between the two. We get smaller off to the right. I don't even care about the left side of the graph. This is talking about negative populations. If we look at a C that is greater than 0, right? And notice we're subtracting off C. So when I say C is greater than 0, that's a vertical shift downwards, even though I'm saying greater than 0, because I'm saying we're subtracting off C. So what I should expect to see happen here then is that we're going to see this guy shift downwards to where there's still technically a region for us to have some population growth, but it's harder now, right? There's a much smaller region where the population grows, a smaller set of populations that are associated with population growth. Finally, if C is much, much bigger than 0, it's just got a negative value for dp dt forever. It doesn't matter how big the population is. If we're harvesting a ton, much, much greater than 0, then we're going to get our dp dt value is always a negative, meaning our populations will always decline. Now remember, this graph's under an axis right here. Remember that population is the x-axis, not the y-axis right here. So this is saying our rate of change is what's our vertical measurement right here. So even if you start at this p-value right here, you are going to just go to 0. There is no, oh, and by the way, I guess I shouldn't well, whatever. I shouldn't be drawing any left sides of my graphs over here. I'm just going to scratch these guys out. Nobody cares about this left-hand side. We're actually doing a real-world problem now. There is no negative populations out there. So let's algebraically find the bifurcations. And I should say, I know there's only one bifurcation. It's going to occur when this is a touching root right there. Well, I just want to go ahead and set my k, p, 1 minus p over n minus c equal to 0. That's my dp dt. I want to find exactly when we have 0, 1, 2 roots. Since it's quadratic, I know I'm going to be able to quadratic formula this thing. So I'm going to get a kp minus, let's see, k over n p squared minus c equals 0. Let's just shuffle some terms around here. K over n p squared. I added that over. I'm going to get a minus kp plus c equals 0. Right? Good with that? Yeah. Negative. Okay, cool. So let's go ahead and take this guy to the quadratic formula then. Then we're going to get that p equals negative b plus or minus b squared minus 4 times a times, and c is literally c in this problem right here, actually, all over 2k over n, right? I don't really care about most of this stuff. I want to know about the discriminant. Oh, right. And I was thinking for a second that I'm solving for k right here. What I really want to know about is what's going on with c. C is my thing of interest right here. So doing a little bit of solving here, I'm going to multiply by n, divide by k. So I'm going to get a k n over 4. Oh, wait, I forgot my c. Equals c. And so it looks to me like I can now kind of form my conclusion here that if c is greater, oh man, I need to fall onto my next page here. I got so close to drawing this all on one page right here. Can't do it. So what we can kind of conclude here is that if we know what a population's growth constant k is, and if we know what the population's carrying capacity n is, it seems like we can literally compute how many is in a sense a safe number to harvest from the environment while still leaving that population with a stable equilibrium that they could live at. If we overharvest, then there is no equilibrium size for that population and it will decay down to 0. All right. So that's kind of a really cool thing that we can do with this kind of population modeling right here is we can determine, in a sense, and now I basically just feel like a massive jerk when I say these things. I feel like such a freaking human when I say statements like this. Like, I hope that everybody's super aware that we're like basically lighting our planet on fire with the amount that we consume its resources, both replenishing and non-replenishing resources. For us to think that we are able to control environmental factors that we really obviously can't control and that are influenced by tons and tons of factors that we don't have a handle on is insane of us to think that we can actually do. That being said, it is the case that there is some level of, for example, fishing that we can do that's not excessively destructive to fish habitats where humans are also still getting some fish. I don't think that there's almost any of those practices in place today at all. Commercial fishing absolutely means that most species of fish that we currently eat will not be available on Earth, even just for our children, just one generation away. We are really close to most of these species that we currently use for most of our food being at the edge of their population collapsing because the amount that we harvest is more than they can handle. The other thing that you should recognize is that as we continue to do things like pollute the environments that they live in, not only is their carrying capacity K getting smaller, meaning that the acceptable C is getting smaller, but it's also the case that a lot of times their growth rate of a population is getting smaller. They're less likely to encounter each other. I don't know, there's just weird things that happen when all these animals experience the pressures of being around humans. I think that humans are both causing our K values and our N values for all of these populations of animals to get smaller, meaning that our pressures mean that it's less acceptable for us to harvest, except since there's more humans, we're actually harvesting more. So we actually are working doubly against ourselves by both taking out more while the population is under more stress with less resources, meaning like there's I mean, most of the things we eat today, we won't be eating in 50 years. Beef, straight out the window. Way too resource intensive. It's going to take one disease, and all the cows on Earth aren't going to be able to be eaten. Fish in the ocean, much less controlled by humans. We're massively overfishing these things. We used to have schools of billions of fish across the Pacific Ocean that now count in something like 10 or 15 million when there used to be billions. Those populations are going to collapse probably relatively soon. It's not like we don't know that these are happening. We've been able to do this math for like 50 years, well before these things were ever a problem. But don't remember, we can make money off of completely eradicating entire populations. And as long as shareholders stand to benefit, we're probably going to do that. So just remember that we understand all of these biological and environmental systems. As a as a species, humans have collectively decided, or at least I should say, Americans have decided that money is more important than their existence. And so I would encourage all of you to think about the fact that like it's not like these are hard problems to solve. We just solved it right here. We know exactly what's well and what's unwell for these populations. It's just that there's money to make by killing all of them. And so we're going to keep on doing that. So think about that every time that we make our future decisions about what we think is best for the population species that are around us and the politicians that we elect that are ultimately going to make those decisions. It would be cool if there was not like half of all species gone from Earth in the next 50 years, but it doesn't look like we are making the decisions that are going to cause that to happen. So that's why I said today is our slightly depressing day. Talking about bifurcations and biological situations is not fun because all it is an acknowledgement of the way that we're destroying our planet. And so I try and say it with a smile on my face because otherwise there's nothing really nice to say about it right here. Um, so so here's our bifurcation discussions for today. You should recognize that a significant amount of this is associated with your ability to do algebra and to go add slider bars to graphs in Desmos. We want to be able to interpret these things and recognize that this is giving us a huge categorical description of long-term behaviors of all of the differential equations in a one-parameter family of differential equations, which is very massive statements that we're making out of just doing a little bit of math from a differential equation. And again, we haven't straight up solved a differential equation in like 4 class periods right now, which is kind of crazy. What we're recognizing is that there's a huge amount of analysis that we can do about long-term behavior of amounts, populations, and stuff like that by analyzing a differential equation without actually coming up with its solution. Now, that being said, our very next video, and that's my answer to you, Freeman, is in our very next video, we're going to be talking about our linear differential equations and our integrating factor. Ultimately, what we're going to do is we're going to look at something with our fuzzy eyes here. We're going to squint at it very carefully. We're going to look far and we're going to look close and we're going to be like, man, lots of differential equations look like they came from the product rule, don't they? That's going to be the statement that we're going to make that's going to get the ball rolling for us in section 1.8. And our question is, how is it that we can take any linear differential equation and force ourselves to see it through the lens of it being the result of a product rule. We want, therefore, to come up with an integration rule that undoes the product rule, right? So it's going to be sort of like an integration technique. You can see this thing called the integrating factor. There's going to be a term that we want to come up with. It's going to be our fixed term. It's going to take something that's almost a result of the product rule and turn it into something that's exactly the result from the product rule, meaning that we can undo that derivative from the product rule to solve the differential equation. And that is going to be how we're going to head into our stuff in the next week here. Um, so that's going to be my. I know that we went a little bit long here today, so I'm going to try and wrap this guy up right here. But we're going to pick back up next Thursday with 1.8, our next analytic solving technique. 1.9, we're also going to get another technique. You should think of it like U sub for differential equations. Take an expression that you currently can't do the math on, make just a substitution of variables, the smart choice, and it'll turn it into something where we become able to do the math once again as U sub does for us there. Happy week 3, everybody. For those of you that were in the chat, thank you. Freeman, it was cool to have you here. I'm going to take a look at your GitHub project here. And next week we'll be back. I'm going to make some more videos next week, Thursday, Friday, to talk about integrating factors and about our substitution rules here. And that'll be our wrap up for chapter 1. I will see all of you guys then. Have a good one.